So, in the last lecture we had considered the problem of unidirectional transport. Into a finite domain. In a Cartesian coordinate system. Okay. So, we had two surfaces, this had the z direction and t is equal to, okay, the top surface at t equals t infinity, this was t is equal to t naught, this was z equal to 0, z is equal to h, okay, and this t is equal to t infinity for t equal to 0. At initial time the temperature was t infinity, and we found that the temperature field has a series of solutions. Okay. As it approaches the steady temperature, okay, define T star is equal to T minus T infinity by T naught minus T infinity. Okay. And Z star is equal to Z by H, and the time is equal to T alpha by H square. And we had got the equation as partial square, sorry, okay. We had separated the temperature into a transient part, into a steady temperature plus a transient temperature, where the steady temperature is equal to 1 minus Z star. The transient part of the temperature we had solved using separation of variables. The transient temperature is equal to some g of T times Z of Z. Okay. And it turned out that if you write it this way, the boundary conditions for the transient temperature Tt transient temperature is equal to 0 at Z star is equal to 0 and Z star equals 1. Okay. There was no the boundary conditions were homogeneous, and the forcing was in the initial condition. Okay. Initial condition T star is equal to minus of 1 minus Z star at T equal to 0. Okay. And based upon that we had got the solution for the transient temperature as summation ai sin I pi z e power minus I pi the whole square t. Okay. I is equal to 1 to infinity. Okay. It can be 0 to infinity or 1 to infinity, it makes no difference in this case. And we had determined these coefficients ai from the orthogonality relation integral 0 to 1 dz star sine of I pi z sine is equal to 1 by 2 delta I j, where delta I j is the Kronecker delta function, is equal to 0 for I is not equal to j, and is equal to 1 for I is equal to j. Okay. Using this we had got all of the coefficients as ai is equal to minus 2 by I pi, okay, and substituted that into this constants and got the temperature field. Okay. This was for a Cartesian coordinate system. Okay. So, let us look at another case where we do it for a cylindrical coordinate system. Another case where we do it for a cylindrical coordinate system. So, we have a cylinder, okay, we have a cylinder of radius okay, of radius r. Okay. Okay. I will call the axial coordinate as x and I will call the radial coordinate as small r. Okay. This is initially at temperature T is equal to T1 okay, at T is equal to 0. Okay. So, at initial time at T is equal to T1, T is equal to 0, the temperature is equal to T1 okay. And it is instantaneously immersed into a bath which is at temperature T is equal to T naught. Okay. Okay, it is instantaneously immersed into a bath for which the temperature T is equal to T naught. Okay. So, basically you have a cylinder at a particular temperature say 50 degrees centigrade and you instantaneously immerse it into water at 20 degrees centigrade and you want to know how the temperature of that cylinder changes with time and as a function of radial position. Okay. So, that is the problem. Okay. So, I can scale T star is equal to T minus T naught by T1 minus T naught. Okay. R star is equal to R by R. Okay. These are the standard scalings for a finite system. This implies that the time scale will be equal to alpha T by R square. The time it takes for thermal diffusion over a distance comparable to R is R square by alpha. So, you scale temperature time by that coordinate. Okay. So, these are standard scalings. And once I do that, I get an expression for the temperature field partial T by partial T is equal to 1 by R d by dr of R partial T by partial R. Okay. So, this is the Laplacian operator in the radial direction for a cylindrical coordinate system. It is different from that for a Cartesian coordinate system. In a Cartesian coordinate system, it is just equal to d square T by dz square. Okay. So, this is different from the operator for a Cartesian coordinate system. Okay. What is the temperature as time t goes to infinity? Okay. What is the temperature as time t goes to infinity? As t goes to infinity, you would expect the temperature to be uniform throughout. Okay. Since you are in a bath at temperature T is equal to T naught, that boundary temperature is not changing. Therefore, in the limit for T going to infinity, the temperature has to be equal, the dimensional temperature has to be equal to T naught throughout the domain, okay, which implies that the scale temperature has to be equal to 0. Okay. So, that scale temperature is the steady temperature. Okay. So, the steady temperature is throughout 0, okay, scale steady temperature throughout the cylinder is equal to 0. Okay. Therefore, I can just write the temperature is just equal to the transient part, okay, because the scale steady part of the temperature is equal to 0. Okay, and you can solve just for the T star alone. Okay. So, for T star, the equation is as given here. Okay. In a cylindrical coordinate system, what are the boundary and initial conditions? Okay. What are the boundary and the initial conditions? Okay. We know that at r is equal to r, okay, T is equal to T naught. Okay. R is equal to r implies that r star is equal to 1, T star has to be equal to 0. Okay. So, that is the only boundary condition. We require a second boundary condition. In this particular case, the coordinate r varies from 0 to capital R. Okay. The coordinate r varies from 0 to capital R. Okay. Therefore, you need a condition at r is equal to 0 in order to solve this problem. Note that at r is equal to 0 there is no physical boundary, okay. There is no physical boundary, and therefore, you can only have a symmetry condition at r is equal to 0. Let us examine how the temperature can vary at r is equal to 0. Okay. Okay. So, if I plot the temperature as a function of r, okay, as a function of the radial coordinate, okay, what can it be at r is equal to 0? This is an axisymmetric configuration. Okay. This is an axisymmetric configuration. That means that if the temperature field coming in one direction looks like this, the temperature from the other direction, opposite direction, has to look something like this, okay, because it is axisymmetric. Okay. The temperature in one direction looks like this, okay, looks like this. The temperature in the other direction has to look something like this. In a third direction, it will look something like this, and so on, based upon the different directions in which you approach the axis of this cylinder. This axisymmetric condition implies that if the slope is non-zero, okay, if the slope is non-zero at this point, that means that the slope is not uniquely defined, because when you approach from different directions, the gradient is different. Okay, the gradient is along the radial direction. However, as you vary the angle around the axis, the gradient is in different directions if you approach the axis from different directions. Okay. The gradient is along the direction of approach, it is along the radial direction because it is axisymmetric. The gradient is along the radial direction. That means that if you approach the axis from different radial directions around the axis, the gradient is different, and therefore, it is not uniquely defined at the axis, okay, if the gradient is non-zero. The only way that it will be 0 is if, okay, the only way it will be unique is if the gradient is equal to 0 at the origin. Okay. If the gradient is equal to 0 at the origin, then you will get 0 regardless of which direction you approach, and there will be no discontinuity in the gradient. Okay. Therefore, symmetry requires that at r is equal to 0, partial t by partial r is equal to 0, which means that at r star is equal to 0, partial t by partial r star, this has to be equal to 0. Okay. Only then will you get the same temperature regardless of which direction you approach the center. Okay. Okay. So, this is what is called a symmetry condition. Okay. Okay. That is, if the gradient has to be the same regardless of which direction you approach the axis of the cylinder, since the gradient is along the radial direction and the radial direction varies as you go around the axis, the only way that you can have the same uniquely defined gradient at the origin is if that derivative is equal to 0. Okay. So, that is a condition that appears out of symmetry. Okay. And the other condition is that at t is equal to 0, right, t is equal to T1. Okay. The temperature is T1 at initial time. Okay. At t is equal to 0, the temperature is T1, which means that at T star is equal to 0, T star equals 1. Okay. So, this is the initial condition. Okay. So, there are two boundary conditions and one initial condition. Okay. Okay. So, there are two boundary conditions and one initial condition. Okay. So, how do we solve this problem? Once again, we use separation of variables. Okay. The equation is partial t by partial t is equal to 1 by r I can expand this out as partial square t star by partial r star square plus 1 by r star expand, write down t is equal to some function f of r g of t. Substitute into the equation and I will get f partial g by partial t star is equal to g into partial square f. These should be total derivatives because one side is only a function of f and the other side is only a function of g. So, I should write this dg by dt star. Okay. Divide throughout by g times f. Okay. Divide throughout by g times f. Okay. Okay. And this ends up being the equation. Okay. And this has to be equal to a constant. What should be that constant? That constant has to be a negative constant because otherwise g will be exponentially increasing in time. Okay. If you want g to be an exponentially decreasing function, okay, then that constant has to be negative. I should note here that the steady solution is just t star equal to 0. Okay. The steady solution is t star is equal to 0. Okay. For the transient part, you can see you have two boundary conditions. Both of these are homogeneous. Homogeneous boundary conditions are where either the function is equal to 0 or its derivative is equal to 0 or some linear combination of the function and its derivative is equal to 0. Okay. So, these are homogeneous functions. Either the function is equal to 0 or the derivative is equal to 0 or some linear combination of the function and its derivative is equal to 0 at all spatial boundaries. Then you have homogeneous spatial boundary conditions. In this case, the boundary conditions are homogeneous. Okay. And as I said, now in this equation, the left side is only a function of t of time, the right side is only a function of radius, and therefore, both of these have to be equal to constants. Okay. Both of these have to be equal to constants. This has to be a negative constant because if you take the part of the equation proportional to g, you have 1 by g dg by dt star is equal to some constant k. If that constant is positive, then g is exponentially increasing in time. Okay. Whereas you require the transient part to exponentially decrease in time, so that it satisfies the boundary condition in the limit as t goes to infinity. Okay. Therefore, this has to be equal to a negative constant, okay, is equal to minus beta square. So, now let us first solve the spatial part of the equation. Okay. So, 1 by f into d square f by dr star square plus 1 by r star df by dr star, okay, is equal to minus beta square. Okay. Multiply throughout by f and I will get a term f on the right side, and I once again multiply throughout by r star square. Okay, multiply throughout by r star square and bring the term on the left on the right side to the left side. Okay, so I will get r star square df by dr star square plus r star df by dr star plus beta square r star square f. This is equal to 0. Okay. Now, how do we solve this equation? Okay. This equation, it is what is called the Bessel equation. Okay. I can redefine a new variable r plus is equal to beta r star. Okay. I can define a new variable r plus is equal to beta r star. You can see the first two terms on the left are unchanged, because I have r star square times d square by dr star square and r star by times d by dr star. Okay. So, this just becomes r plus square d square, I should note a square here, plus r plus df by dr plus r plus square f, this is equal to 0, okay, plus r plus square f is equal to 0. Okay. This is a particular case of the Bessel equation. Okay. So, the Bessel equation is of the form x square d square f by dx square plus x df by dx plus x square minus n square f, this is equal to 0. Okay. So, this is the Bessel equation for integer n. Okay. Okay, this is the Bessel equation for integer values of n. Okay. This one is a special case of the Bessel equation for n is equal to 0. Okay. This one is a special case of the Bessel equation for n is equal to 0. Okay. The solution for the Bessel equation is f is equal to a times j n of x plus b times y n of x. Okay. These j n and y n are two functions which I will discuss in a bit. Okay. J n and y n are two different functions which I will discuss in a little while. Okay. So, therefore, the solution of this equation is going to be equal to f is equal to a times j naught of beta r star, r plus is beta r star, plus b times y naught of beta r star. Okay. That is going to be the solution for the Bessel function, Bessel equation. Okay. And what are the form of these solutions? Okay. What are the form of these solutions? Okay. So, if I plot the function j naught of x, y naught of x as a function of x, j naught has an oscillating form, oscillating, but the amplitude of the oscillation decreases as x increases. Okay. And it crosses the x axis at multiple different locations. Okay. It crosses the x axis at multiple different locations, and it has 0 slope. It is actually has a value 1 at x is equal to 0. Okay. At x is equal to 0, the value of j naught is 1. Y naught, on the other hand, goes to minus infinity at x is equal to 0. Okay, y naught goes to minus infinity at x is equal to 0. So, these are the two solutions of this differential equation for n is equal to 0, of this differential equation for n is equal to 0. Okay, so, these are the two solutions. Now, the solutions for my function f is a into j naught of beta r plus b into y naught of beta r. Okay. These constants are determined from the boundary conditions that T star is equal to 0 at r star is equal to 1 and partial T star by partial r star is equal to 0 at r star is equal to 0. Okay. This second condition is satisfied by the function j naught of x here, it has 0 slope, but the function y naught has an infinite slope at the origin. Okay. Okay, y naught goes to minus infinity here. Okay. This function y naught goes to minus infinity here, therefore, it has a infinite slope at the origin. Okay. This implies that for this particular case, this constant b has to be 0, otherwise this function will diverge at r is equal to 0. Okay. So, therefore, I get from the bound symmetry condition at r is equal to 0, I get this as a j naught of beta r star. The second condition I require is that T star is equal to 0 at r star equals 1. Okay, the second condition is that T star is equal to 0 at r star is equal to 1. That means that this implies that j naught of beta is equal to 0. Okay. And this j naught of beta equal to 0 is satisfied at multiple locations, because as I said, this is an oscillating function with a decreasing amplitude. Okay. Therefore, this is satisfied at multiple locations. Okay. So, the first few locations where it is satisfied are beta 1 is equal to 2.404, beta 2 is equal to 5.520, beta 3 is equal to 8.654, and etc. Okay. So, there is a series of points, this beta 1 here, beta 2 here, beta 3 here, etc., where it is satisfied. Okay. Therefore, this value of beta can have multiple values. Okay. Recall that when we did the Cartesian coordinate system, we required that sine of beta has to be 0 and beta was equal to I times pi, where I was an integer, and there were multiple values of this of I for which this was satisfied. Similarly, there are multiple values of beta for which this is satisfied. Okay. So, therefore, I can write this as a j naught of beta n r star. Okay. And then I have to solve the other part of the equation, 1 over g dg by dt star is equal to minus beta square, which implies that g is equal to e power minus beta n. Okay. So, the most general form of the solution is of the form a j naught of beta n r star e power minus beta n square t star. Any beta, any value of n for which beta n is j naught of beta n is equal to 0 satisfies the equation and it satisfies the boundary condition. Therefore, the temperature, the most general form of the temperature is the summation n is equal to 0 to infinity. I have taken 1, so I will take it as 1 to infinity of a n times this. Okay. So, you have a series of functions. Okay. You have a series of functions. The first one looks something like this. Okay. That is this one where this is equal to 0. The next one looks something like this. Okay. So, this one beta n corresponds to this. The third one looks something like, okay, all of them at r star is equal to 1. This series of functions is equivalent to the sine functions that we had in a Cartesian coordinate system. Okay. So, these are the basis functions, okay, and I will continue this in the next lecture. These basis functions also have orthogonality relations. Okay. These basis functions also have orthogonality relations which can be used to determine what are these coefficients. So, that I will continue in the next lecture. I will complete this part of separation of variables in a cylindrical coordinate system. So, I will continue this in the next lecture. I will see you then.